Let's continue with the topic waves. Okay, I was talking about an analytical treatment. Okay, analytical treatment for a stationary wave. Okay, let's look at this. Let's consider one wave to be y1 is equal to a sine omega t minus kx, another one to be a sine omega t plus kx. You can consider this as capital A or small a, it's your wish. Okay, but why, you might ask me, why didn't I put a negative sign in this? There's one more derivation in which I taught you in the class where I did a sine omega t minus kx, and where y2 was a minus a sine omega t plus kx. To indicate that, so when I put a negative sign before this x component, it shows that the wave is going from left to right. Okay, when a wave is going from right to left, I put it with a plus. Where here again I'm doing the same thing, a minus here and a plus here, which is fine, but why have I inserted negative sign in this? What are these two case study, a case study 1 and a case study 2 imply? Okay, now I'll finish it and then tell you. In this, y is equal to y1 plus y2, where you take a out common, sine omega t minus kx plus sine omega t plus kx, and so it's like sine a plus b plus sine a minus b is 2 sine a cos b. Whenever I get like this, the component omega t shows that this should be taken and this should be brought forward, because that represents a wave, correct? And so this is the maximum amplitude. So then you're doing a case study on this maximum amplitude. The maximum amplitude is 2a cos kx, in which if you're going to locate nodes are when the amplitude is equal to 0. Nodes are the points at which the amplitude will be 0 in a stationary wave. Now, these are nodes. These are the nodal points at which the amplitude is equal to 0. So applying that here, I get a cos kx to become 0. And when will cos kx be 0? When kx are the integral multiples of a 90 degree, a 3 pi by 2, a 5 pi by 2, a 7 pi by 2. So then the angle kx is 2n plus 1 into pi by 2. Now what is k? K is a propagation constant, which is 2 pi by lambda is equal to 2n plus 1 into pi by 2, where pi and pi gets cancelled. From this you can write what is x, it's 2n plus 1 into lambda by 4. So you just put n is equal to 0. You get n is equal to 0. It's lambda by 4. X is equal to lambda by 4. Then put n is equal to 1. You get 3 lambda by 4, and n is equal to 2, you get x is equal to 5 lambda by 4. These are the points at which I'm getting the nodes. Then let's look at antinodes. Antinodes are the ones or the points in the stationary wave where the magnitude of the amplitude is maximum. These are the antinodes. Antinodes. Okay, so you understand what is an antinode stands for, and for which you know that the amplitude has to be maximum, and a 2a cos kx has to be maximum. Then cos kx value has to be plus or minus 1, and it occurs at a rotational motion. Take it at 0, at pi, a 2 pi, a 3 pi, a 4 pi. So you can say kx is equal to n pi. And k is 2 pi by lambda into x is equal to n pi, where pi and pi get cancelled. X is equal to n lambda by 2. So putting n is equal to 1, x will be lambda by 2. Putting n is equal to 2, x equals lambda. Putting n is equal to, what about putting n is equal to 0? N is equal to 0, I'll get x is equal to 0. N is equal to 3, I get x is equal to 3 lambda by 2. Therefore, I understand these are the points at which my antinodes occur. So when I draw a stationary wave here, I'm going to draw. Let's try drawing like this, a cos graph. Let me try it. This is also a stationary wave, right? Only thing is the starting point is an antinode. Okay, so I'm just trying to see if this correlates to what we did. X is equal to, at node, first node occurs at lambda by 2, lambda by 4. First node occurs at lambda by 4. Can you see this wave is 1/4 of full wave. A full wave is this. This is what in a stationary wave is termed as lambda. In a progressive wave, this is termed as lambda. In a stationary wave, this full thing is termed as lambda. We have this, which is 1/4 of lambda here, the red color that I've drawn. So, correctly at the first node occurs at lambda by 4. Correct? So, the first node occurs at lambda by 4. The next node occurs at, can you see there is a 3/4 lambda? This portion is cut, so it's about 3/4 of the wavelength. Okay, so 3 by 4 of lambda. It's perfect. So from this point, if you see, this occurs at lambda by 4. This occurs at 3 lambda by 4. 3 lambda by 4, and obviously 5 lambda by 4, and so on. And let's talk about the antinodes. At the first antinode occurs at x is equal to 0. Then the next antinode occurs at x is equal to lambda by 2. Can you see? This will be lambda by 2. And this will be lambda, one full wavelength. Can you see? This is one full wave. As you can see here, this is like this, one full one, another half. And this half and this half makes it one, so one full wavelength. I hope you get it. So then this is what it is. So you really understand. And so you can put it here. This is x is equal to 0. This node occurs at x is equal to node lambda by 4. This antinode occurs at lambda by 2. This antinode. This node occurs at 3 lambda by 4. This antinode occurs at lambda. So that like that you can x is equal, you can just correspondingly put all this and you get the answer. Okay, so this is the analytical treatment. And you obviously get your maximum amplitude as cos, and so when a cos graph at 0, it has to be like this, the graph has to be like this, and it starts with an antinode. Whereas in other treatment, this one, I was considering a string in which there is a wave which progresses like this and comes back as like this. A crest is getting converted into trough. Okay, so in that case, you have to take this as one is positive, other is negative, whereas x is always negative. Okay, so you understand that for the going forward, it's minus kx, for returning it's plus kx, but the y value is becoming negative. The y which was forward, it was positive, for reverse it is becoming negative. That is the reason in this case we are mentioning it like this. And so in this you need to do analytical treatment y1 plus y2. You get a into sine omega t minus kx minus sine omega t plus kx, which is like sine a plus b minus sine a minus b, which is sine omega t minus kx minus sine omega t plus kx. So this is like sine a minus b minus sine a plus b, which is coming with a minus sign, and a 2 cos a sine b. In this, the omega t factor is with a cos, so take it to the other side towards the end. So minus 2a sine kx and then a cos omega t. So this becomes your maximum amplitude. So you're going to do an analysis in this using a 2a sine kx. So when so this is your maxima, which is at 2a sine kx. The maxima can be plus or minus, so you can ignore that. And for nodes, you know that similarly the amplitude has to be 0 when sine kx has to be 0. When will sine be 0? at 0, at pi, at 2 pi, 3 pi. So kx is equal to n pi at 2 pi by lambda into x is equal to n pi. Pi and pi get cancelled. X is equal to n lambda by 2. Putting n is equal to 0, you get x is equal to 0. N is equal to 1, you get x is equal to lambda by 2. N is equal to 2, you get x is equal to lambda, and dot dot dot. Okay. And now for antinodes. So those were for nodes and these are for antinodes. For antinodes, you understand that the sign kx has to be plus or minus 1, which occurs at 90 degree, 3 pi by 2, 5 pi by 2. So odd integrals of so kx can be 2n plus 1 into pi by 2. So k can be written as a propagation constant 2 pi by lambda into x is equal to 2n plus 1 into pi by 2, where pi and pi get cancelled, x remains as it is. So you can write what is x, therefore 2n plus 1 into lambda by 2. So in this case, when n is equal to 0, you get x is equal to lambda by 2. Lambda by here 2 lambda by 4, right? Lambda by 4. So then n is equal to 1, you get 3 x is equal to 3 lambda by 4. And can you see this whole condition is getting reversed here? Okay, so and that was for nodes, and here this is for antinodes, so the positions. Okay, so this is the way you and you know for that matter that this is a sine graph, and the stationary wave starts like this at x is equal to 0. So that's the variation between the first one and the second derivation. I hope you're clear. So what else did I miss teaching you? Let's see. The medium through which the wave is traveling. What are the properties that the medium should generally possess? The medium should possess elasticity, then should possess friction, then it should also possess and inertia. These are the three things that any medium should possess in order to for the wave to propagate. Okay, so that's about this. I hope I in the previous video dealt with how is the wave velocity different from the particle's velocity, and those are all very important questions. So now that you learnt analytical treatment of both the cases, you should also understand that there are certain laws of transverse vibration. Laws of transverse vibration in a string. What are the laws? First is law of length. Okay, you know that the velocity is inversely proportional to length. Okay, let's see. Velocity is in Bayer, it's tension by mass per unit length, which is termed as m. And so when you call it as mass per unit length, this length goes up, right? So that's known as law of. That's not going up though. Fundamental. That's the frequency, not the velocity. I'm sorry. I hope you're clear. It's not velocity. We are talking about frequency. Frequency is inversely proportional to length. Let's see this. We know velocity is directly proportional to length, and you know mu is equal to v by lambda. So you can write v to be mu into lambda is proportional to L. Therefore, mu is directly proportional to L. I hope you can remember this. So in terms of velocity, you think, but when you talk about a fundamental frequency. The fundamental frequency of a vibrating string is inversely proportional to length, provided all other components such as tension and mass per unit length remains constant. Okay, so that's first. The second is law of tension. Law of tension is, it's directly, velocity is directly proportional to root of tension. We know that. So we can say frequency is also directly proportional to root of tension, provided the length and the mass per unit length remains the same. Fundamental frequency is directly proportional to. So let's go next. Next is law of mass. Law of mass, we know in velocity is root of t by m, where m itself is mass per unit length, is inversely proportional to m. The frequency is also inversely proportional to square root of m. Provided all other components such as mass per unit length and what else, tension, all remaining to be a constant. So let's go next. Law of mass is over. What about law of diameter? So law of diameter, you know velocity is root of tension by a mass per unit length. Okay, and in this mass can be written as density into volume. Density into volume. Volume is area into height, which let's call it as L, and L get cancelled, and the area is pi r square, which is d by 2 the whole square. So then therefore when we say it's d comes out, and therefore velocity is inversely proportional to d, therefore the fundamental frequency is also inversely proportional to capital D. This is known as law of diameter, provided the mass per unit length and tension, all of them remains a constant. Length and density also, they're saying length and linear density only, no? Okay, so just leave it like that. Then law of density. Law of density. And in many of this, we know that there is eta by rho, that's the square root of rho, so velocity was like that. So frequency, fundamental frequency is also proportional to square root of density, provided the tension, mass per unit length and all remains constant. Okay. Tension, length and diameter. Provided tension, length and diameter. They are not saying mass per unit length because density has got mass. So they didn't open the mouth about mass per unit length. The tension, in this what are the constants? Tension, length and diameter remains same. For diameter, it was tension, length and density is remaining to be the same. For mass, it was mass per unit, for mass, this is mass per unit length. No, how is it? It's mass only. This itself is mass per unit length. So therefore, only the length and tension has to be the same. So this tension, so say mass per unit length is remaining the same. So whichever component, you just make sure these things are quite different. Just make sure you're memorizing those and writing it. So let's go to next. That what did I teach you was about an organ pipe. So next thing that I taught you was about an organ pipe. In an organ pipe, you know that there will be a small place where it's called mouthpiece, where you have actually draw it like this and draw like this. Okay. So here you draw a beveled portion B. Make sure it's beveled. Okay, so then let's continue. There's air column throughout. But what happens when you keep your mouth here and blow? This gets reflected like this after touching the bevel. It gets deflected so fast. The air comes in jet speed and comes and strikes this place L, which is called the lip. This portion L is called the lip, and this is called the beveled portion or beveled. And so then when this jet air comes and falls in the lip starts vibrating. And so then there is a particular frequency of vibration. There will also be some air column which manages to travel through in here. And there will be a frequency of vibration for this frequency and that frequency are equal. That's when a large sound is produced. Okay, this small frequency with which the vibration is resulting in something called an edge tone. And the sound wave travel down the pipe and get reflected as it is closed. If supposing it's closed at one end, it will get reflected and produce a stationary wave. And that stationary wave is going to produce a vibration and frequency which is equal to the edge tone. That's when a loud sound occurs. The person who is playing the mouth organ can just blow a little bit of air itself. But due to this phenomenon, a loud sound is being created. So I hope you understood that. You can always look for the details in Aurora once again. So then now let me talk about an organ pipe. This is an organ pipe. So let's talk about an open organ pipe. In an open organ pipe, both ends are open. So obviously antinode only will be created. So this is the entire length of the tube, and as I told you, 2 oval shape is 1 lambda. So here there's just half of this, which is just this portion, and half of this, which is just this portion, which means it's lambda by 2. Therefore lambda 1 is equal to 2L is my equation number 1. Let's continue to draw. At the open end, you'll always have antinode. Let's draw 2 nodes next. Just draw it like this, draw it like this, draw it like this, draw it like this, draw it like this. So you have, let's compare it with the full wave. You have one full wave here, yes, and you have one half, another half here, which is this. So entire length of the tube is equal to lambda. That's my lambda 2. Lambda 2 is equal to L is my second equation. Let's go to third one, in which you can have 3 nodes. Antinode, and you can compare this with one full thing. Can you see a 1 and 2? This is one full wavelength, and there is a half wavelength. These two together makes, this is 1/4 and this is 1/4, they make it half, so 1.5. So 1.5 is 3 by 2, so we can say the entire length is occupying 3 by 2. Lambda 3, so lambda 3 is 2 by 3 of L. Equation 3. Once you write this, you can start writing the frequencies. Okay, you know the frequency mu is equal to C by lambda, or in other words V by lambda. V itself is like in air, it's gamma P. In a string, it's tension. So in this case, it's only air. So I would write it as gamma P by rho, and there's a 1 by lambda 1, where in the case of lambda 1 is my equation 1, which is 2L. So I can write it as 1 by 2L into root of gamma P by rho. That will be my fundamental frequency, mu 1. It's called fundamental frequency or first harmonic. Next you can do mu 2, where it's velocity by lambda 2, and this is always gamma P by rho, and 1 by lambda 2, and lambda 2 from the second equation is merely L, so you can write 1 by L. For if you want a good symmetry, because there's 2L, you can always multiply and divide by a 2. So now mu 3 is equal to V by lambda 3, 1 by lambda 3 into root of gamma P by rho, and our lambda 3 is nothing but 2 by 3 of L. Lambda 2, lambda 3. Lambda 3 is 2 by 3 of L. So you see 2L, but 1 is to 2 is to 3. Can you see? There's a 1 is to 2 is to 3, and this is called, the second one is called second harmonic or first overtone. Next one is called third harmonic or second overtone. So then the frequencies mu 1 is to mu 2 is to mu 3, or 1 is to 2 is to 3 progression, and that is the reason it's called harmonic progression. Harmonic progression is you learned arithmetic progression, geometry progression. This is another progression which is like 1 is to 2 is to 3 is a harmonic progression. So this is about an open organ pipe. Next, let's deal with the closed organ pipe. Analytical treatment of open organ pipe is also there. There is also analytical treatment for an open organ pipe. Isn't it the same as what we did before? Let's see. We already took the open organ pipe, which is similar to this one. An open condition is similar to this analysis, correct? And you know that the maximum amplitude was determined by cos kx in this. The whole equation x can be replaced as L, that's the only difference. You can repeat the same derivation here also. And you can say that the determining factor is just cos KL instead of x. Because the entire length of the tube is there. and you equate it to plus or minus 1, and that's for an antinode, as you know. Okay, and equal to obviously for an antinode, and equate it to 0 for a node, and thus you know for an antinode a k into L is equal to cos antinodes occurs at the maximum amplitude, and the maximum amplitude of cos occurs at n pi, and k itself is 2 pi by lambda is equal to L into 2 pi, where pi and pi get cancelled. Entire length of the tube itself is n lambda by 2. And so then when you put n is equal to 1, you get L is equal to lambda by 2. N is equal to 2, you get L is equal to lambda. Isn't this the same case that we studied for antinodes here? L is equal to lambda by 2. L is equal to lambda. It's the same. There I was doing it with a drawing. Here I am justifying with by means of writing the derivation. However they want, you can present it. That's what it is. Okay, so you can continue to write the same derivation after this, because the same, you know what is lambda, how does the lambda get replaced as length, you know from here also. So you can write the same thing, and you can write the same derivations back again. So this is the condition for antinode. Similarly, you can write the condition for node also, which is just a repeat of the previous one. Cos kx is equal to 0. Cos kl is equal to 0. This occurs at kl is equal to 2n plus 1 into pi by 2. 2 pi by lambda into L is equal to 2n plus 1 into pi by 2, where pi and pi get cancelled. L is equal to 2n plus 1 into lambda by 4. When you put n is equal to 0, n is equal to 1, you get the same conditions for the nodes that we discussed. Okay, so but we just discussed here only about length. Okay, so then that's about it, guys. Don't worry too much. Right, whatever derivation I taught you now is closed organ pipe. Here you know node will only occur. Node. So first case is like this, and you know this is lambda by 4. So lambda 1 is 4L. Next case, one node is here, another node has to be here. And you know this is 3/4 of the wave. So entire length has got 3 by 4 of lambda 2. So lambda 2 is 4L by 3. Next case. You know one full wave is here. Apart from that, you have a lambda by 4. And lambda plus lambda by 4 is 5 lambda by 4. And that 4, entire length of the tube, you have 5 lambda by 4. So lambda 3 is equal to 4L by 5. So like this you write what is lambda, and then write mu 1, mu 2, mu 3. Mu is equal to V by lambda. Again it's gamma p by rho within root, and 1 by lambda 1, which get replaced as 4L in this case. So a 1 by 4L into root of gamma p by rho. Second case is V by lambda, where it will become root of gamma p by rho. 1 by lambda 2, what is lambda 2 stands for? It's 4L again, but 3. And so you notice 1 is to 3 is to, next will be 5 obviously. You can write it by guessing it, you don't have to even scroll up. Okay, so you can write 5 by 4L into root of gamma p by rho. And so then therefore you can say mu 1, and this again is called the fundamental frequency, the first harmonic. Next is second harmonic or first overtone. Third harmonic, second overtone. So these frequencies pair, and mu 1 is to mu 2 is to mu 3 is in the ratio 1 is to 3 is to 5. So that's the part about a closed organ pipe. And so in this, there's a major mistake that I did. This is called Since it is 3, it's called third harmonic. Note the point. This is called fifth harmonic. So there's a variation. Okay, I didn't mention this earlier. So because it's odd harmonics, okay, you can't call it as second harmonic. In the case of closed Rauten's pipe, very, very important point. Hope you noticed that. Okay, so next is, so please make the necessary correction. I cannot amend the video now. I'm bad at it. So make sure you make those changes. And if they ask you analytically, they wouldn't. But if they ask you analytically, you know, it's you remember this one, the right side, whatever I did. The analytical treatment for a crust becoming a trough. Yeah, this is the treatment. And in this, you know, the maximum amplitude is sine kx. And as usual, you apply that and you can justify it. So by means of drawing also, you can justify it. It's up to you. So next is, next, what did I miss? Oh, it's still here that I have taught. I didn't teach you beats, but I'll just manage to put that in this video.